1 minute, just in case you want to push to YouTube, because I don't think you are. But otherwise, I will get going. Yeah, there we go. Perfect. Okay. That's it. Let me know in the private chat about the timing. I'm going to probably make it more or less an hour. But if I need to catch up on the time, that works too. So yeah, thanks for joining. I'm sorry I couldn't make it in person. I've only been to India once a few years back in Bangalore, and I would love to go back. Actually, it was probably like in my top 3 of the best travel experience ever. I think it's getting late for you guys. It's still the middle of the afternoon here in France, where I'm dialing in from, and I want to talk to you about Zephyr. You might have heard about Zephyr maybe earlier today already. You will certainly hear a bit more in some of the following sessions. But yeah, it's going to be a really high-level overview, 45 minutes overview of Zephyr. If there are any questions, feel free to chime in, just like in the room, ask the questions. I don't think I have audio feedback, but just get someone to type them in the chat, and I'm happy to be interrupted pretty much any time during the course of this presentation. So it's going to be mildly technical. It's also about like presenting sort of the whole ecosystem around Zephyr and what is Zephyr in the first place. Some of you might have experience with things like Arduino, or like just generally speaking, you may have been doing some embedded development and embedded programming. What Zephyr is, in a nutshell, is an RTOS, a real-time operating system that can be used to write embedded software that's effectively super portable and that can target a wide variety of use cases and applications, all the way from the really, really small battery-powered, maybe wearable kind of devices, all the way to really, really big, like wind turbines and anything in between, like laptops. Maybe the main brains of a laptop is effectively a pretty big microprocessor, but there's lots of microcontrollers that are supporting the laptop when it comes to doing things like what happens when you're in standby mode and you still need to do things like charging the battery or monitoring like maybe network activity in the background while the main operating system, Linux or Windows, whatever, is down. There might still be some software components that are running, and those are typically running in really, really small and constrained microcontrollers. And yet they want to you want them to be pretty efficient, pretty secure, and that's something that Zephyr can effectively enable for you. And yeah, like I said, it starts from the really, really small, tiny wearables kind of devices, just a few kilobytes of, tens of kilobytes of flash, let's say, and a few kilobytes of RAM. And it might not do much when you have like such constraints, but that's how you end up powering things like, again, wearables or control algorithms in smart thermostat, things like that. And yeah, yet, however small it can get, you can also take it to much bigger systems, and you can compose bigger systems and bigger applications. You can use like multi-core approach for things that are maybe more complex. You can deploy like wireless sensor networks, and that's pretty much the beauty of Zephyr. It's meant to be really, really flexible. So which is something that's quite challenging, because at the end of the day, what Zephyr does is providing you with all the things and the services and the programming framework, if you will, that's going to help you build an embedded application without having to reinvent the wheel, and bringing you lots of independence towards the underlying hardware platform. Like when you start writing the control algorithm for some kind of smart thermostat, you don't want your code to have hard dependencies to this particular Bosch temperature sensor that you're going to use at at day one, because things might change. Like in a year or two, you might end up using a different sensor from Siemens or whatever, and you don't want to rewrite your code and your logic just for this small change, right? So that's, and similarly, you may want to change hardware architectures altogether. Maybe you started your prototype on an ESP32 kind of device. Some of you might be familiar with that, but you want to switch to an ARM-based MCU from ST Microelectronics, maybe. And how do you do that without having to rewrite all your software? So yeah, lots of portability and lots of, security is a key concern for many, if not all, embedded application and embedded use cases. So Zephyr is effectively built with safety and security in mind. And we will talk about that further throughout the presentation. I should have mentioned that all those sort of like pillars and key elements, they are in no particular order. So in no particular order, Zephyr is also open source. You probably knew that already, but yeah, it's a project that lives under the umbrella of the Linux Foundation and has for the past 7 or 8 years now with a super active community and ecosystem that effectively help take Zephyr to actual commercial products, right? It's just like the Linux kernel. It's way more than just some open source code on GitHub that people can just take and do whatever they want with it. The whatever they want aspect of it is effectively building actual commercial products. And so we will dive into some of the technical sort of details of what Zephyr is in the first place. What is the stack, if you will, that you get when you start using Zephyr? But in a nutshell, it's like I mentioned a bit already. It's this sort of abstraction layer that you need to build on top of microcontrollers and on top of embedded hardware, and it's, the same kind of abstractions that you would find in the Linux kernel, if you will, in the form of abstracting out interactions with all kinds of sensors, interaction with storage devices, etc., except that it's meant to run and to fit where Linux is too big. Again, I mentioned just a few kilobytes of RAM, tens of kilobytes of flash. You don't get Linux in those kind of targets, right? So yeah, that's sort of in a nutshell. And one key aspect beyond just providing the really low-level services and the kernel, if you will, it's also about providing the entire connectivity stack and connectivity layers. When you think embedded, when you think IoT, Internet of Things, you think connectivity. You want to build a wearable that's going to be Bluetooth and Bluetooth Low Energy. You want to build some kind of asset tracking device that's going to use NB-IoT and cellular networks to report a GPS location every 2 hours or so. So this connectivity stack is actually like, it's a key part and a core part of the Zephyr stack and the Zephyr ecosystem. Similarly, connectivity for you might mean USB. You are building a PC and a computer peripheral that's going to effectively be some kind of super fancy mouse or some, I don't know, but you're going to need to implement some USB device stack. Zephyr has one already for you that you can reuse. And everything is in Zephyr, all the way from the documentation to the actual the tool chain and the actual code base is really meant to be developer friendly. And it's actually pretty nice to develop Zephyr applications like some of you will get a chance to experience in the workshop later today or tomorrow. But yeah, you have tons of tools available for writing the code, debugging, getting some nice overall developer experience. Lots of products are running Zephyr today, and kind of double clicking on what I mentioned before, it goes all the way from the really small wearables, or even like we have small tracking devices that end up being put within and inside Rhino horns so that you can track in real time the position of the rhinos, so that you can potentially send someone like a ranger to help in case you detect that someone might be in the process of poaching the horn and the rhino for the horn. So that's really, really small, but you would find also Zephyr running in the bottom right of the slide. You would see Vestas wind turbines. So those really, really huge wind turbines, they have Zephyr on them to do monitoring of the whole electrical system. So that's pretty cool. When it comes to building an application on top of Zephyr, just like I mentioned, some of you might be or might have played with Arduinos in the past, might have played with the Espressif ESP32 product line, maybe with MicroPython, all those kind of like developer-friendly, DIY-friendly environments. Obviously, they support dozens of boards. Zephyr probably supports even more because effectively there's over 500 boards that are supported and running Zephyr. And if you have a close look, you will actually find and see in this small subset of the list of supported boards, some that would typically be Arduino boards, some that would typically be ESP32, some that are just random ARM boards from Nordic Semiconductor, STM32, and XP, and there's many, many others. And so, again, looking at this slightly more closely, Espressif, STM32, and there's even a few RISC-V based boards on the chart. Those are actual different, very, very different hardware architectures, and yet the same Zephyr applications, you can write code that would run on any of those boards effectively. Similarly, you're super independent from the hardware, and like I mentioned, like you care about monitoring the position of your device, of your smart device. You're going to use some kind of accelerometer. You don't have to write the driver, right? Just like in Arduino, you would reuse an existing library. You would do the same in Zephyr, except that it would actually provide you with even more facilities and abstractions to make really the most of the sensor without having to bother writing low-level code. You would really just focus on the high level, like what is really your application logic, if you will. So I mentioned that already, but highlighting maybe a few more that I didn't get to mention in this slide just before the previous one. Many, if not all, the typical hardware architectures you would find on small and constrained devices are supported. They're super common ARM, probably equally common Extensa that you would find on the good old ESP32 boards and Wi-Fi and Bluetooth chips, but also Intel and MIPS and RISC-V and many others that you might not even know existed, like ARC or Spark, which are more geared towards some like very specific, sometimes safety critical, sometimes industrial grade kind of scenarios, but all those have Zephyr support. And beyond the code, it's also an ecosystem, which we'll dive in towards the end of the presentation. But I'll touch a bit about how the project is organized and what are some of the cool things that are sort of gravitating around the open source project and some of the cool commercial products that you could find out there that are effectively using Zephyr and have for many, many years. Diving a bit into the technical stack, and I need to do a quick time check. I think I'm already 15 minutes in. Let me see. Yeah, not even, but I have the timestamp in the chat, so it should be good. I guess I'm going to go until the top of the hour, pretty much. The stack. So it's probably really small for you guys, maybe even super pixelated. So let's just dive right in into the stack. We could start, depending on how you want to approach it, we could start with the very low level layers like the core kernel, multitasking, scheduler, etc. I should probably start that way, but since connectivity is such an important aspect of the whole Zephyr story and the whole quite frankly, like for all the embedded operating system, one way or the other, they care about connectivity, because these days, pretty much every device ends up being connected one way or the other. Might not be connected to the internet, might just be some kind of like LoRa network or thread or Matter. But connectivity is important, and it turns out Zephyr supports a wide variety of communication protocols. The list is not even complete when I say Ethernet and 802.15.4, Thread, LoRa, Bluetooth, CAN bus. That's just really a small subset of what's supported. The kind of more high-level protocols, things like TCP/IP, UDP, CoAP, MQTT, HTTP, WebSockets, like you name it. It's likely that it's already supported in Zephyr if you need it. Some protocols even more geared towards IoT scenarios, like lightweight M2M, which is a lightweight protocol for connecting and monitoring devices over the air, doing things like remotely upgrading the firmware of a device. How do you do this and that in a standard way? Rather than reinventing the wheel, you can leverage the existing lightweight M2M standard and get make sure essentially, and that's a key aspect that we will actually talk more about, which is security. An embedded device historically, bringing connectivity to the embedded world might be seen as a problem in some industries or for some applications, because you have maybe more of an attack surface when it comes to, giving bad actors a door to enter your system. But hopefully the trade-off between this and the fact that you actually get way more value by being able to send your sensor data to a server and things like that. Hopefully the trade-off is in the favor of the latter. Plus, there are ways to, since you are connected, there are ways to effectively keep the devices up to date, so that whenever there is a vulnerability in the device, you can actually roll out a new firmware and a new version of your application without necessarily having to go on site and flash a new application onto whatever conveyor belt or whatever it is that you've built, and whatever is the embedded product that you want to update. Diving a bit more into the connectivity aspect, IP, like I mentioned, is really there's a full-blown IP stack in Zephyr, and without necessarily going into all the bullet points, you have the second bullet point, which is effectively all the sort of the companion protocols that you typically find in the TCP/IP world, like SNTP and NTP for talking to time servers, DNS for doing name resolutions, etc. Like they are part of the stack, including IPv6 support. So that's one bullet point that's important. Another one is the fact that in many cases, we see people, and that might be your case for whatever project you have in mind, with whether it's at school or anywhere really, you have existing code that was meant to run on Linux and that does networking stuff, and you probably, if you're familiar with and if you've done that in the past, you probably have used BSD sockets, right? And that's kind of like the standard way to implement communication between different hosts and different nodes. And this kind of like standard way to approach socket communications, and beyond that, even like things like semaphores, etc. Like there's a standard BSD API that Zephyr exposes. So any code that's been written against BSD sockets effectively runs on Zephyr, so that's pretty cool. And something else, the fact that back to the first point, something that's important and that's pretty much true across the entire stack. The network connectivity stack in Zephyr is native in that it's been written by Zephyr and for Zephyr, if you will, which means that it integrates with all the key concepts of Zephyr, namely, and maybe most importantly, things like power management. Like Zephyr has this nice way of making sure that whenever the device, the small, potentially and probably battery device, has nothing to do, because I mean, your application is maybe just about reading data from a temperature sensor every 30 seconds and sending the data to the internet. Or maybe that's not even that. It's acquiring data every 30 seconds from the temperature sensor. And then only every hour you would compute the average and the moving average of the temperature, and that then connect it to the network. And so you want the operating system effectively to just automatically take care of going in standby mode whenever you as an application developer have nothing to do. Then the OS should already know that it can put the networking stack to sleep. And by that, it means probably also putting the actual network interface and the network controller, like the piece of electronic that takes care of doing Wi-Fi or Ethernet. It will effectively power it off or put it in standby mode, and that's going to be automatic, and that's integrated way down the stack, the connectivity stack, but also all the other like driver layers of Zephyr. Bluetooth is another option. So for this one, like I don't want or need to go necessarily into the details, because what I would encourage you all to do is, if you have a device at hand that does Bluetooth, like Nordic boards or ESP32 dev kits, they happen to have a Bluetooth chip. They happen to be supported in Zephyr, and there are tons, like literally dozens of samples that you can find in the Zephyr repository to tinker with some of the cool Bluetooth APIs, Bluetooth and Bluetooth Low Energy for, I don't know, like you want to build some kind of health tracking device and expose heart rate and whatever else over Bluetooth and over standard Bluetooth profiles and whatnot. This is supported in Zephyr. Or you can even do like things like 6LoWPAN and have and like build mesh networks and on top of Bluetooth. There's lots of really, really cool stuff. And my advice would really be to just go and check out the many, many samples that are available in Zephyr. Just try and run them, look at the code, and have a lot of fun, basically, because Zephyr, because Bluetooth is a lot of fun. It's a really, really rich stack and ecosystem. Bluetooth Low Energy more specifically. Don't want to necessarily go into the details there. Just like try out the samples, read the documentation for the various boards out there to see what's supported. But there are some really, really cool use case for also doing things like, back to the firmware upgrade thing that I was mentioning before. You may be interested in doing remote firmware upgrade of a device over Bluetooth Low Energy, right? From your smartphone, you push a new application update to your smart thermostat or things like that. It's definitely something that's supported. USB, that's also, I mean, if you are really into building some kind of IoT/embedded device, USB might be relevant. You might want to expose, you might want your device to behave as an actual device stack. Expose, I don't know, behave as a USB stick, USB mass storage device. Whenever you plug it into a laptop, something should show up in the virtual hard drive, or it should show up as a mouse. It should show up as whatever, as an audio device. You want to build some kind of gadget that does audio, that's supported as well. So that's pretty cool. And might be the other way around. You might want to talk to USB devices, and you can do that as well. Power management, I think I mentioned that in the context of the network stack and the IP stack, but just in general, Zephyr RTOS, the OS in RTOS is really for operating system, in that in the background, should you enable it, it's always optional in Zephyr. That's something that needs to be very much highlighted, actually. If you can afford it, if you care about it, you just enable the power management features. What that will effectively mean is that in the background, there will always be some like power management daemon sort of going on and paying attention to what are the different tasks running in the system, and should there be nothing to do at a particular point in time, the device will automatically realize that, oh yeah, well, I mean, all those sensors that my application is typically using, my Wi-Fi chip, etc., if we're going to be sleeping for the next 29.5 seconds, I might as well put everyone to sleep and just wake everyone back up right before the deadline, right? And so that's something that the scheduler and the power management stack effectively does. When it comes to building an application with Zephyr, there's something that's being leveraged that comes straight from the Linux world, which is a way to describe in a fairly human-readable and very structured way, describe the capabilities of the underlying hardware and configure the underlying hardware. Like if you take two variations of an ESP32 dev kit, they might be pretty similar in that they might both use the same actual SoC from Espressif. They might be coming with this exact same set of LEDs, same temperature sensor, but they might have like a different memory layout. Like, I mean, one is maybe $2 cheaper than the other because it uses a different memory chip. Describing all those potentially subtle variations between different flavors of the hardware is something that you can do thanks to the device tree, and you see an example here on the slide. But effectively, you describe all the capabilities of the hardware, the memory layout, like should you have sensors being made available over specific buses like I2C, API. Those are all things that would be described pretty much like once and for all, statically, when you build and describe your application. And then at compile time, this device tree gets turned into everything that's needed to properly initialize the system for you behind the scenes. If your device tree describes a particular temperature sensor from Bosch, then automatically the build system will pull the proper driver and will make sure to initialize the driver with whatever settings and parameters you've declared through the device tree, right? So that's, whoops, sorry about that. That's kind of like the high-level idea behind the device tree. Security, just in a nutshell, one thing that Zephyr allows to do, again, optional, but pretty easy to leverage and to enable, should you care about it, and you should probably care, is the ability to have effectively a custom bootloader in your system that makes sure that when your device starts being shipped and is sort of like in production and deployed out there in the field and in the wild, making sure that your system can only boot and will only boot and start up if the firmware that you're trying to run is signed by a trusted authority, you basically, and making sure that people cannot really sort of like compromise your application that way, or cannot try and like roll back the application to a previously vulnerable version of the device. So that's those capabilities are there. There's extensive documentation about leveraging things like MCU boot, or doing things like remote firmware upgrades, like I mentioned earlier, using protocols like lightweight M2M and others. Security also goes like it's just the secure bootloader aspect, but there's also, just generally speaking, you might want to leverage hardware cryptography in most, if not all, embedded systems these days. There's always some kind of dedicated IC integrated circuit that would expose APIs to perform cryptographically secure random number generation and things like that. And so you would find the drivers for that in Zephyr as well. POSIX, I mentioned POSIX. I don't think I need to, hopefully the point was clear enough. Zephyr exposes a POSIX API so that if you have code that's been written against POSIX, doing socket read, socket write, listen, accept, bind, whatever, like threading, semaphores as well, mailboxes, whatnot. This is there, this is supported, so you can take existing code and run it. But it goes also the other way around in that Zephyr applications can run natively on Linux. Zephyr, just like you can run Zephyr on ARM, you can run Zephyr on Espressif, you can run Zephyr on whatever. You can also run Zephyr on a POSIX/Linux operating system. And natively, the Zephyr Hello World or whatever Zephyr application, really, you can just run on your machine. And that really, really helps when it comes to debugging and testing your application, because you don't even need actual Arduinos or whatnot. You just test and run code on your machine. So the OS in RTOS is for operating system, and the RT is for real time. In that, one thing that you probably want to use Zephyr for, again, you don't have to. You might just have one thread, one task in your entire system, and yet you would still be able to leverage some pretty cool features from Zephyr, but usually you would leverage multitasking, and there's very minimal overhead when it comes to actually, although you are running on super constrained systems, you can still have sort of the comfort and the sort of the high-level abstraction of multi-threading and tasks and semaphores and whatnot, so that from programming your application sort of perspective, it feels like you're doing something that's more modern than what you would usually find in the embedded world, where it's more like I have an infinite loop, a super loop, and I do everything in the loop, and I manage all the timings, etc. by myself. With the RTOS, the timing and the scheduling, it's taken care of for you by the OS itself. A few other things that are like, we're getting really, really high up the stack now, but again, that would be some code samples that you can find in the Zephyr repo. You can play with graphical user interfaces. Like, if you're super constrained, you probably don't even have an LCD display in the first place. But if you do, and if you care about building a graphical user interface with potentially a touch panel as well to manage touch interactions, this is integrated as well. And so you can build your next smart thermostat or smartwatch, including the display and the touchscreen. That's something that you can do as well. IPC, inter-process communication. I should have maybe moved that slide to the to go just before, but yeah, all the point here is just to say that all the modern ways that might exist and that you might be familiar with to deal with inter-process communication or inter-processor potentially also communication. Those are all available to you, either like the low-level kind of historical ones like the FIFOs, LIFOs, mailboxes and pipes that you would find more coming from the BSD and POSIX world. There's also things like ZBus, the Zephyr message bus, that is way more advanced in that it's effectively a full-blown message bus with one-to-one, one-to-many communication capabilities. And again, tons of code samples available for you to try out. Developer experience, I mentioned that early on. like whatever IDE you feel like you want to use, you can use it. VS Code is a good one, but you can use Eclipse, you can use CLion, and you can use also tools for doing advanced tracing and debugging. Like you want to dive into like the actual RTOS internals and making like trying to figure out why you seem to have deadlocks between your different tasks and whatnot, some like priority issues, etc. You can effectively get all the traces from the kernel and debug applications that way. And the screen capture that you see here is showing showing just that, like different tasks, showing when each task is active, when each task is more like in a pending mode, and that way you can figure out performance issues or even like deadlocks. Zephyr 3.4 was just released, so just a few, just released. Actually, we are closer to 3.5 now that we are to 3.4. But the point here is just to say that there's a lot happening. I'm actually due to post my Zephyr weekly update in just a few hours. Every week, I try to post news about what's going on in Zephyr. There's literally hundreds of commits that get merged from one week to the other. So there's lots of cool new features that always keep getting added. So those are a few that were added for 3.4, and there will be probably even more actually for 3.5. But all the way from new drivers to, of course, new supported ports, etc., etc. So I'm going to try and speed things up a bit. The next few slides are slightly less technical, but still nevertheless super important. Safety and security. Not like every other open source project out there. I mean, some would have those kind of concerns in mind, but not all. Zephyr does care a lot about safety and security and making sure that people can build real, actual commercial products on top of Zephyr. And so we do releases every 4 months, but similar to Ubuntu and others, every other year we would create long-term support releases that are meant to be supported for at least 2 years, right? And so that's we try to have sort of like a dedicated branch where the long-term support release is being maintained on the long run, and people who feel like they want to build a product that's not going to, that's going to live and be deployed in the wild, they will probably decide and go with the LTS version rather than the the one that gets released every 4 months. Supported for 2+ years. I think that's kind of like the bottom line here, and the thing that you need to keep in mind. Let me see. I'm going to try and go slightly quicker. And safety. So safety is also an important aspect. For something like Zephyr, obviously there's thousands and thousands of lines of code and functionality that's part of the repository. But the core of Zephyr, like the scheduler, and what makes really the operating system that ends up being used for like potentially safety critical stuff. Like if you use Zephyr to build the algorithm and to power an ECU in a car to deal with the braking system or the steering wheel or I don't know what else, it's effectively safety critical. So what the community is doing these days is working on identifying really what is the core and minimal kernel of Zephyr, and like with things like thread APIs and the scheduler and things like really basic functionality, but the kind of functionality that you really want to make sure that it works 100% or 200% as intended and as specified as per like high-level requirements. And so this whole certification process is something that's currently happening. And the goal is really to make sure that further down the road, people who want to take Zephyr and build safety critical products on top of it, they already have a good starting point in terms of knowing that the building blocks they are building on top of are effectively like follow some best practices and safety related international standards to ensure that it's effectively safe, or as safe as can be. Yeah, and with that, I mean, like those final slides, I might go through them rather quickly, because hopefully we can find a few minutes for questions. But the way the community is structured, maybe as opposed to a random, again, GitHub project that you could find here or there, Zephyr is effectively a Linux Foundation project. So member companies, like the ones that you see here on the slide deck, join the Linux Foundation and join the Zephyr project as members to help steer Zephyr in hopefully the right direction for the years to come. And those platinum members that you see here, or the silver members here, they are all involved in deciding where to invest, like safety, like I mentioned, security are really critical aspects. The overall onboarding and developer experience for Zephyr, making sure that whoever is interested in using Zephyr will have a great experience with it. This matters for pretty much all these folks, because Google, for example, they build and they use Zephyr within the Chromebooks. So they have effectively engineers working on porting Zephyr, building applications on top of Zephyr. They do care a lot about Zephyr because it's going to be in their laptops for the foreseeable future. And for them, it's important that there is that Zephyr is overall healthy, because that means that, well, they are running software that works well, but that also means that they get to when they need developers and engineers that are knowledgeable about Zephyr, it's more likely that they will find some on the market if the community is really, really healthy. And if we, as the Linux Foundation and the Zephyr project, we help the community to be where it needs to be. So that's the whole story there about the ecosystem, all the way from all the development tools that you might want to use, the IDEs, the emulation environments. You don't want to use, you don't have an Arduino or an ESP32 at hand, you use Renode, you use Walkway. This is all, I mean, yeah, there's probably many logos that we're missing there. Similarly, you need some help in getting training about Zephyr. There's options there, companies that can help with giving you services and consulting around all things Zephyr. All the libraries that happen to be, there's a lot that's effectively available in Zephyr proper. When you get the code from our GitHub repo, many libraries would already be pre-integrated. But there's many more that are available out there and that happen to play well with Zephyr, some of which are mentioned here on the slides. You want to do robotics, you may want to use ROS. That would be an option as well. Yeah, and we're just getting started in a way, because if you look at Zephyr versus other real-time operating systems out there, open source real-time operating systems, whether you look at it through the number of contributors, the number of supported boards, supported drivers, it's pretty impressive actually. So that's every on a 30-day period, any 30-day period in the recent past in Zephyr, you would have at least 250. Because I mean the graph needs to be updated, but between now and a month ago, or between a month ago and now, there's 250 plus individuals who ended up contributing to Zephyr. That's a lot if you think about it. It's many commits every day, every hour, every month. It's thousands of commits every month. And that's way more than many of the other RTOSes out there. Many of them actually even combined probably don't even make up for this amount of activity. People seem to like Zephyr as well. Many GitHub stars, it would appear. And yeah, that's actually doing quite good on timing, I think, hopefully. I have time for questions, which I can take either now, either later on. I can stick around in the chat, or people can find me. I didn't put my contact info, but maybe you see me. You see my Twitter handle on my video stream. Yeah, I'm Cartben on every social media out there, pretty much. Rudra is actually asking a question on live on YouTube. Is this Debian based? No. In that we are talking microcontrollers and we're talking really, really small devices. So it's effectively way lower level than a typical like Linux environment. It feels like Linux in some ways. Like if you're familiar with Linux development, things like device tree, like I mentioned before, might ring a bell. Things like kconfig to help with making your code base easy to, more modular and easy to configure. Those are concepts that we borrowed from the Linux world, but otherwise the stack itself is it's not Debian. It's really like it's Zephyr, but you can use Debian and Ubuntu as your developer environment. That's for sure. Like when you go through the Zephyr getting started from either of the first two links, you can quickly navigate to the Zephyr getting started. The first step will be to instruct you how to install the Zephyr SDK and Zephyr toolchains and whatnot. And most people would typically do this on their Ubuntu machine or Linux. So yeah, those links, I mean, they speak for themselves, hopefully, but main project website, the GitHub repo where you can engage. If you find a bug, if you have an idea for a contribution, like you've been putting together a driver for a sensor that wasn't supported in Zephyr, that you would like to see supported, you can submit a pull request. We have many mailing lists that you can use as well, but I would actually recommend, rather than using the mailing lists, use our Discord. So chat.zephyrproject.org will give you the invite link to join our Discord channel, where you have tons and tons of activity, and any question you have will likely get answered in 5 minutes, 10 minutes. That's how active it is. Are there other questions in the room on YouTube? You're welcome, Rudra. Okay, well, again, you can find me online. You can find the entire community online pretty easily. And yeah, thanks for having me. Thanks for the attention. And enjoy the rest of the event and the conference.
Hi. Great. Do I get started? Start presenting? So I have uploaded the files already. Is that what I can use? Okay. Can you see my slides? Okay. Fantastic. Let me see if I can go back and forth. Yes. Okay, cool. Okay. We can start. Yes, go ahead. Okay. Hello, everybody. My name is Shiva Khan. I'm a kernel maintainer and Linux fellow at the Linux Foundation. Today, I am talking to you from US remotely. Sorry, I couldn't be there in person. Someday, I would love to be there and see all the sites, including Sundarbans. That's my list of things, must-do things someday. All right, so let's get started. I'm going to be talking to you about getting, as I said, getting a start in open source. So as you have seen in this conference earlier, Zephyr being a Linux Foundation project, and then how it is an open source project and how people come together and participate in development and administration and all of those other aspects of the project. So as we all know, it's no secret, open source runs the world, and we have it's pervasive: technology, media, financial, healthcare, medical, telecommunications, and agriculture, and it's only growing. You will see it's being used in travel, energy sector. We have a project, LF Energy, that oversees Linux in using Linux and Linux ecosystem in energy. AI, we also have LFAI, and social media, right? Your phones, they won't run without Linux, Android, and others. So you name it, it's there, it's everywhere. So we all know code doesn't write itself. Yeah, not yet anyway. So, with we are able to write essays probably with the ChatGPT, but we can't write code yet effectively. And who is who in open source? Let's look about, we think about coders a lot, right? When we think about open source and open source projects, software projects, we think about developers. But there are a lot more players in addition to developers. Maintainers play both roles, both developer and maintainer roles, meaning maintaining the aspects of the project, accepting the code, and what should go in, what shouldn't, and all of those maintainers take care of that. And there are legal expert community builders that take on the role of building out communities, making sure communities stay healthy and sustainable. And educators, a lot of the mentors that come in. Benjamin that talked about Zephyr, for example. He's playing the role of a mentor at this point, sharing the project details with you, so get you started in the project. And all important users that use the projects themselves. So let's step into, with that introduction to open source, let's step into how do you get started in it. It is no different from starting on any starting in any technology or a field. It becomes a difficult because you do not have a central place to go to and start. You will have, there is a central place in the code base is your central place, but then you interact with lots of different people, and each community has a different culture and a different way of communicating with the community, and different way of contributing to the community. So it's always a beginner's problem. Where do I start? A journey of 1,000 leagues starts beneath one's feet. So you have to take that very first step. How do you do that? The very first step is identifying what you're passionate about. What do you see yourself doing 5 to 10 years from now? Maybe a long-term, 15, 20 year rest of your career. And what do you enjoy doing? Do you enjoy writing code? Do you enjoy debugging problems? Do you enjoy understanding the concepts and teaching others what those are? And do you enjoy managing the project in terms of releasing, taking care of releasing aspects, making sure the quality is good, validation, and so on. What are you passionate about? And once you kind of identify those, you also keep thinking about which project is right for you. It could be Linux kernel for some people. It could be Zephyr for some others, or it could be CNCF or Hyperledger or networking, all of the other higher level projects, right? So operating system takes you down into the lowest level possible, other than firmware and building hardware, of course. So how do I get started? So once you decided, okay, this is where I want to be, or this is where my place is, how do you get started? So the code base always looks complex. You look at the code and you go, oh, this looks really, really complex. Where do I get started? And community also looks intimidating. You do not know who they are. You just know their email addresses and you are following their discussions and on the mailing list. And where do I start learning? That is always the questions, the very first questions that come up, and it appears to be, it is overwhelming. It is overwhelming. So once you decided which project, and then you decided, okay, this is the community, and you have been following the community for a bit, and then you go, where do I find resources? Because you do need resources to learn. And who can help me with the questions I might have? Who can I reach out to ask the questions that I have as I am learning? So this is what I call the what, how, where, and who question. First of all, what area you want to be in, and how do I get started, and where do I go to look for resources, and who can I reach for help? So this is where mentorships come into play. The Linux Foundation to keep injecting new talent, injecting new diverse talent into our open source ecosystem. We have started Linux mentorships roughly about 5 years ago. I'll talk about getting into the specifics of what we offer in terms of mentorships and resources, but I will talk about the role of mentorships and what they bring to the table in terms of for new developers as well as maintainers and experts in the communities. What do they offer? So a structured, well-defined program to attract and develop next generation. So if we want the communities to stay healthy and sustainable in the long term, which we know is important because we have seen that open source runs the world. So we have to keep attracting and developing next generation of new developers. What does that mean? A well-trained diverse talent is very important. So the best thing we can do is having experts in the communities train them. So by bringing new talent in, we are not only strengthening the project and the community, we are also bringing new ideas in. So that is diverse ideas are new and diverse ideas are very important. And another thing mentorships do is they provide learning opportunities and resources. We all learn differently. So with keeping that in mind, providing self-learning resources that can cater to a wide variety of learning needs is important. So what does it do for experts and mentors? It gives an opportunity to teach and share their expertise. What I have learned in mentoring and teaching and learning new things as I go along, if I explain something new to somebody, something I know to somebody, I get a deeper understanding of that subject. So mentoring plays a role, and sharing expertise plays a role in enhancing the knowledge we have ourselves. So another thing by mentoring, you bring new people in to the project, and then they can help you with the work that needs to be done on the project. And it is also an opportunity. You can train people in the ways, so you're not constantly training new people or answering the same questions. So you can have a set of training materials and do that to have them available. So for the new developers and mentees, what are the benefits? They can learn from experts, and then they can learn collaborative skills. Open source collaboration skills are very, very different from a team oriented skills that you might learn on a closed source projects at companies. They are very different. You have to think about what's best for the project, the open source project, as opposed to what's best for my product. So it's totally a different skill set. Collaborate and working with open source communities is something that that is learned over time. And if you are learning those skills, so technology, learning those skills in a mentoring environment, it's always good. So what happens is technology is easier in a lot of different ways. Working with people and being able to work with the community at large, and how to work with the community, and how do you make contributions, those are all very different in different open source projects. It's almost like each open source project has its own culture. So being taught by experts in that community, you get a leg up right away. And finally, after learning from experts and learning to collaborate and work with them, you can become open source contributors. Yes, I talked about that network. So another big thing you gain is especially if you are doing a career transition, say you are working in different other fields and you want to get into technology and you want to get into, say, Linux kernel community, for example. That's where I come from, so I tend to talk about that more. Then once you participate in a structured mentoring program, you have a network formed. Your peers that participated in the mentorship program with you, and then also the community that knows that you are working on this mentorship program and you are contributing and as a new developer. So you form network, those connections, professional connections. And at the same time, you can network with communities and prospective employees. And keep in mind, all the experts and maintainers in these communities, they do work for companies, and then they do have influence on hiring and so on. So by working with them and forming those networking and connections, it becomes helpful as you advance your careers. So at the Linux Foundation, we look at these communities look at diversity as not just Linux Foundation part, Linux kernel itself, and we look at the projects, communities to keep them healthy and sustainable, that we have to keep bringing new developers from all over the world into participating. So diversity, what does diversity mean to us? Mean to me, anyway, personally, is gender diversity, geographical, language, and ethnicity. So language is an interesting angle here because having worked with people, myself, English being a second language for me as well, I understand that English is not the same everywhere. So you have to adopt a language, inclusive language, where you're not speaking specifically a certain something that phrases and such that are well understood in one region. Like, for example, we say in North America, rubber meets the road. We mean that when we develop a feature or a new API, that until we start using it, we do not know what is it all together, right? So that's where rubber meets the road means. It's a automotive phrase that says until you start driving the car and the tires meet the road, you don't know how it's all working together. But that phrase is not familiar to everybody. So you have to come up with a different phrase when you are working in global open source companies. So it is more than communication becomes very crucial and very important. So what does diversity mean? It's not just having a seat at the table, but you have to be having a voice at the table. If you have 10 people sitting at the table, you want to be able to all the 10 voices heard. So that is what diversity is all about. Another aspect is that equal access to resources is important. Access to resources is a barrier for a lot of people. Resources can be any number of things. Knowing where to find webinars or blogs or material that you can learn from. First of all, having access to a particular hardware that you can use to get involved in a project. And it could even be internet access, if you think about it. Not all places have equal access. But we can do what we can do. We are designing mentorship programs with that in mind, that equity, access to resources is a barrier. So once we know all of these things, that how do we empower, keeping it in mind that we are catering to people across the globe, people that are from various places on various countries and regions of the world. How can we empower learning? It needs to be thought through on how one could learn, and different learning styles, how much time they might have available, and how can they go about taking control of their learning or have an agency on the learning and empower their learning. So how do we do that? Part-time mentorships, webinars, and training. Resources enable women and people with work-life balances, not that maybe they are doing career transition. They have a full-time job they need to get done. They have everything that they need to get done as they are responsible for several things at work, but they are also looking to advance their careers. How do they do that? So part-time mentorships and having offline learning resources will help them. So we have effective learning pathways. The way I envision, as I was putting together this program 5 years ago, I thought about how would I want to learn. A lot of this, I channeled my own experiences on getting started in the Linux kernel development, how I went about finding resources while I was working full-time. So I channeled all of that into designing the pathways, and also leveraging what we already have at the Linux Foundation. So we already have training courses that you can take. Both some of them are free of charge. You can do that. And you can, more importantly, on the Linux Foundation learning site, a training site, you can go and design your pathways. So do you want to be a system administrator? Do you want to be a DevOps, for example? Or do you want to be a Linux kernel engineer, a Linux kernel developer? So you can design your pathway based on the training courses. And then we have several webinars and blogs that we make available. So that's kind of forms the layer of the learning resources I'm talking about. This would be what, how, and where. So this kind of makes the basis, answers that question of where can I find resources? So then once this kind of helps you even some cases by going through this process of going through the exercise of learning pathways on the Linux Foundation training site. You can kind of figure out, hey, maybe I'm interested in this one. Maybe I'm interested in this one. You can kind of look at the webinars and do your research. And then once you have an understanding, then you know that there are a variety of mentorship programs available for you to take advantage of. And these mentorship programs are full-time and part-time. Open for all. When I say open for all, we don't require the participants to be students. They can be employed. They could be working. If they can make time for their advancement and dedicate some time for them for that, they are welcome. And then we also have paid. We pay for your learning, and that's why that's a mentorship concept as opposed to internship concept. So you're actually getting paid to learn, and some of them are credit only. So to be able to offer this opportunity for a large number of people as a scope, we offer them credit only. And then we offer them in spring, summer, and fall, and it is all remote work. You can be anywhere in the world. That's where the world concept comes from. And once you have people that graduate from the mentorship programs, they get connected to prospective employers. How do we do that? We hold mentorship showcases once a year. And at those events, the graduates talk about the work they have done and the skills they have learned, and we connect them that way. And there are other ways you can connect diversity scholarships to events. Speed mentoring at these events also is something that, as a bigger umbrella of connecting and sustaining and communities and empowering new developers, comes into play at the Linux Foundation. So hopefully you can see this little bubble that popped up. More importantly, at the bottom of this pyramid, really, you are looking at maintainers, developers, holding up that pyramid, saying that they are providing all the learning resources and training. Without that, it will be difficult to provide these kinds of mentorship projects and opportunities. So you can, to start with, you can also come, there are mentorship, LFX mentorship showcases. They are on the YouTube channel. So you can kind of go, they're archived, 2022 and 23 are archived. So you can kind of take a look at different areas. It is a kind of a learning experience as well. It is in itself is a learning resource as graduates are talking about what they have learned. Okay, so I covered all of these things as I was talking through. So the part-time open to all, we run 3 terms, spring, summer, and fall. And spring and summer, usually, at least the ones I run the Linux kernel bug fixing project. That one I run spring and summer as both part-time and full-time. For fall, I don't. It's only full-time. Full-time is 3 months, 40 hours a week. It is flexible, it's remote. So we recommend 40 hours a week. For a part-time, we run it for 6 months. Essentially, it becomes 20 hours a week. That's why it runs 6 months. So you can learn from experts in interactive webinars. I'm giving links here so you can walk through that. We have a large number of webinars. We do webinars at least once a month, sometimes twice a month, depending on the availability, how mentors come in. The ones I coordinate and make available, they are primarily Linux kernel and some open source content. And then we talked about LF training, lift scholarships, and plan your learning paths on the training website. So events too, you can come and attend any of the events going through the LF events diversity scholarships. And finally, I talked about LFX mentorship showcases. So this is a quick snapshot of all the things I talked about, resources where you can go plan your learning up here, and then LF Live mentorship series. You can go listen to, we have probably about 40 of them already archived since we started this in October of 2019, I think, or 2020, I don't recall. At least we have 3 years worth of material there in various kernel topics such as fuzzing, dynamic testing, and then all different kinds of testing, and how to debug remotely, and RCU, locking, tracing, and you name it. There's multiple out there. And Rust, we have done several on the Rust. Okay, so let me see, wrapping up here with all the, so mentorship showcases, this is where we connect. We don't leave people once they graduate and say, you're on your own. So we try to connect them with people as best as we can. And then you can see a quick look at what kind of projects are available. Linux kernel, Elisa, Hyperledger Foundation runs their mentorship programs. Cloud Native Foundation runs their mentorship programs. LF Networking, and KDLP is a Red Hat sponsored development program. They work with UMass, University of Massachusetts, and they run one of the their courses, regular courses, and then they have them sign up for this as an extra credit, where they can learn Linux kernel, how to participate in the community, how to get learn kernel concepts and beginners concepts, and participate in the community. Okay, eBPF, and then FINAS, risk, and then this pretty much we have lots of projects. And then summer is usually a great time, because summer tends to be the time when a large percentage of the majority of the foundation projects and the start mentorships, and even others coming and participating, like KDLP and others that come in and run. RIT runs some project. This is Rochester Institute of Technology. So, okay. So thank you so much for your time. Looks like I have a question. Can you explain? Let me see. I can't see the, looks like, okay. Maybe I need to get rid of my slide set here. It's overlapping. Can you explain a bit about the LFX mentorship program? Also, I didn't get a chance to read the whole thing. So I am a mentor in the LFX program. Can you, okay. Okay. So what you do is, you can apply on the Linux Foundation. I provided all the links, by the way. So just follow the Linux mentorship program link, and then create your profile and check the projects, available projects. If you look for projects accepting applications, you will see a list of projects, and then you have to just apply. It's easy to apply. And then each project will have its own screening process. Once you go through the screening process, and they'll tell you the skill sets. Once you create a profile on the Linux Foundation mentorship, Linux Foundation mentorships, then they suggest projects. They'll say, hey, these are my skill sets. And they'll say, okay, these will be your matches. So they pop up the matches, and then you can look at the matches and just apply. And then the working part, it's a remote work, like I said. It's some of the FAQs. I popped up some questions that I get asked frequently. Is this remote work? Yes, it's fully remote work opportunity. Length of the program, 3 months full-time, 6 months part-time. So mentors tend to be flexible about other commitments you might have. The best time I would recommend starting is probably your junior year in undergrad. I do see freshmen applying, but I think that you can probably, depending on your skill set, some individuals might be all ready to go, but in the freshman or sophomore year, meaning first year and second year. But third year probably would be the right time, and maybe the fourth year, because that's when you're looking to graduate, and then having those fresh connections, all of those fresh right before you look for a job, that would be important. That could be beneficial. And 20 hours part-time, and 40 hours is full-time. Okay, so any other questions? I'll open it up for questions now. So there is a 6-week application process, screening process we call. If you're looking for an opportunity in spring, January, mid-January would be a good time to look for what's out there. And for summer session, about mid-April, and then for fall session, about mid-June, July timeframe to look for opportunities there. Even though we do have projects starting off schedule, that's also available. But yeah, that's. So I left some notes here so you can read through them. What can you expect during the project and so on. So that's, you can read through those. So another aspect of connecting people is I sometimes, the projects I run, mentor, which is Linux kernel projects, when people apply, I look for what work they might have done previously. And if there is something that, if they share some research work they have done, and if I find that work that can be shared, and if they agree to share it, I enable them to publish blogs on LF blog site, and we also publish on the news stack. So I do that. If I see a candidate coming in and they already have done some work, otherwise at the end of the project. So they have an opportunity to go in depth, writing a mentoring style, tutorial style blogs and publish them. Okay, that's all I have. Thanks, everybody, for listening to what I have to say today. And I hope this session has been useful to you all.
Is muted. Okay, can you hear me now? Yeah, I'm audible. Okay, perfect. Yeah, then let's get started. So hello, everyone, and thanks for having me here at IIT Mandi. Unfortunately, I cannot be there in person, so we'll try to make this a remote workshop, which can be a little challenging, but I think we can try. We can do this. I work as an embedded engineer at FITech in Germany, And there's also a Phytech subsidiary in India, in Bangalore. And today we're doing an interactive workshop on Zephyr. Shout out to Akashan as well. He's handling the real boards, and with the Robotics and Computer Club, he can help you during the workshop as well as afterwards to set up the environment and get started on Zephyr. Okay, so what we're doing is first I'll give you an introduction of how to get started. I think most of that has already been covered by Benjamin in the talk earlier. We set up the development environment together. Then there are some examples, applications and products. And we will finally do some hands-on examples. Like we will go through some samples. I'll show you in the console how it looks and how you can compile and run those samples. We can keep this interactive. So let me know if there are questions. Keep them in the comments, or I think if there's a microphone, I'm not sure if it's working now. If there's a microphone, then feel free to interrupt me. Microphone is there? No mic, okay. Sure. But yeah, leave comments in the comment section if I have to pause, if you want to give the audience some time to try it out, to install their setup, then let me know. Okay. So what is Zephyr? I think we can mostly skip this part because it has already been covered. It's much more than an operating system. It's a whole IoT infrastructure. And it's ideal to build IoT products on top of it. How to get started? There are great getting started guide, so we can go through that quickly. There's a long list of supported boards and instructions on how to get them up and running. And of course, there are many samples. And actually, all of the samples are taken from the samples from the Zephyr project. I didn't want to reinvent the wheel, and I took the samples from there so that we can have a look at them. I chose some samples where I think they make sense to show as a starting point, to show the capabilities of the operating system. Yeah, then let's have a look at the getting started guide. There should be some USB sticks where you can just copy the SDK and one GitHub repository, a Git repository already. That way you can reduce the download speed. So okay. Bit difficult to get feedback. So are there some USB sticks, and are you trying at the same time to install it, or should I hold on for a minute that everyone can be getting the data? Okay, distributed, great. Yep. Okay. Then we can go together to the quick start guide, and feel free at the same time to try to set up your environment as well. And if you have the files already, then it should be relatively quick and can easily get started. So first, there are some prerequisites, like some Python and CMake and some packages in Linux which you can install. That would be this command. In macOS or Windows, it looks a little different. So in macOS, you need brew as a package manager. And in Windows, this example shows Choco, to install the packages. And there is an instruction here on how to install Chocolatey. So it leads you to the website, and you need to download it and install this Chocolatey package manager on your Windows laptop. And afterwards, you can install the packets. Okay, there's a question from Uta. Yes, we're building Zephyr later. I'll go through the setup guide. So we set up the environment, and afterwards we're building Zephyr and trying out examples. Okay, so Zephyr runs on all the operating system, Ubuntu, macOS in M1 or the ARM version, as well as the x86 versions and Windows. So then afterwards, we have dependencies from Python that is fairly easy to install and should be very similar on all platforms. West, for example, is one meta tool from Zephyr. So it has been developed from the same community, and it keeps track of all the modules and the repositories and downloads them in the beginning. And we need to install West before setting up the environment so that West can now install all the dependencies. So up to here, I installed it already on my system. I think I'll continue until we build one sample, and then we can pause a little until you can set up the environment and maybe ask questions already in between. So we can copy this command, West init Zephyr project, and I'm now going to my console here. I hope you can see that. And we use the same command, West init, but we don't want our home directory. We want to have it here in this exact folder. So now we can see West is starting to download the Zephyr project from GitHub. It will take some minutes now. It will download the code, and it will unpack it and install, in addition, some modules. A little bit more zoom, okay. Is this better? Okay, that is that step. Afterwards, we go into the Zephyr project directory, which has been created now, and then we type West update. Update means it will now check all the modules, check whether they're up to date. So with ls, we can see here, there is a folder, Zephyr project. And here we can see there's the Zephyr repository. But as of now, there's nothing else. So we need a little bit more. So for that, we need to make West update. And now you can see there are some modules. For example, this could be hardware abstraction layer from different silicon vendors. It can be third-party projects which are collaborating with Zephyr. Maybe you can raise your hands for whom is this working as of now? I mean, someone already set up their environment? Okay, let's see. Most are busy, so I take this as a good sign. Yeah, if this takes too long now, I have a copy, so we can just use that. I think we'll do that. So this is a folder which I set up before. So this is the Zephyr project, and this is how it looks after West update. Usually when you have the USB sticks, you will have this kind of repository. Like you have Zephyr repository as well as the modules and all the other tools you need. And this is packed as a zip file. So you just need to unpack this in a folder Then install the Zephyr SDK. And then you should be good to go to run the first samples. Don't forget, later, if you want to connect a real board, like a real board or any other development board, you need to install the UDEF rules, especially in Linux, to get permissions to run and connect to the USB. Okay. Then we can go back to the presentation once. Yeah, this is what we already covered. We have different requirements. It runs on all the operating system. Requirements are CMake and Python, for example. Then Python requirements itself, the Zephyr SDK that provides tool chains like GCC, GDB, ULib, and all this is. Okay, a bit more zoom. I think that was for the console earlier, right? Okay. Yeah, then Benjamin already mentioned that Zephyr has a wide range of samples, and samples can be small code examples that run on themselves, and they're located in Zephyr samples, and they show an isolated functionality or feature. If you want to write an application later based on samples, you typically combine several samples, integrate them together, and by that way, creating an application. Then there are tests as well, which are also kind of small samples. They're used for Zephyr's test automation, and they're also isolated test cases for a feature or for a hardware. Every sensor, for example, accelerometer, typically has a test case where you can test exactly this sensor. They're useful to test device drivers. And applications are not part of the Zephyr repository, but there are interesting applications you can find online. For example, there is one project, ZWatch. It's an open source smartwatch, and you can check the GitHub repository. And yeah, it's a smartwatch, an open source smartwatch with open hardware and open firmware. And you can have a look at how an application architecture could look like with Zephyr. Examples for other projects or companies running Zephyr would be wildlife tracking and protection with the OpenCollar project, in wind turbines, for example, Vestas, or in hearing aid. There is another talk tomorrow at 6 p.m. from Best Sensor, why Best uses open source in Zephyr. And that is a project which uses Zephyr in wastewater pump monitoring for Deutsche Bahn ICE trains. Okay, let's come to the hands-on examples now. I prepared copied different examples from the Zephyr directory. Let us first hello world to check if all the environment is set up properly. Then logging examples, explaining work queues, showing a shell, how you can run a shell and how you can run custom commands. Then we will run a temperature sensor, and finally test Bluetooth Low Energy and connect it with a mobile application. So again, there are different ways to set up the repository with REST, as we just did already. And you can, in the presentation slides, there's also a link on the online platform. I uploaded a link to a GitHub repository. It's called Zephyr Workshop. And in this repository, you can find all the slides and the samples in source code. So you can download it and check it from there. And there are two ways of setting up the repository. One would be to directly initialize this repository with REST. And the other way would be, as we just did, type REST init And then afterwards, you need to clone this repository in the Zephyr project folder. You'll do that now. So coming back to the console, we have here the Zephyr project folder where the basic Zephyr repository and samples and everything has been set up. And into this repository, we're now cloning the Zephyr workshop repository. Okay, that is double. Now we can see it here, Zephyr workshop. And in order for all the requirements being matched to the Zephyr workshop repository, there is one more step you need to do. You need to change the West config manifest file. West organizes the repositories based on a manifest file. So we can change the path of this file to the path of the Zephyr workshop. Zephyr config manifest path Zephyr workshop. You can also have a look at the manifest file. That is it's a hidden folder. It's in .west and then config. And here you can see it's showing manifest, and it has it's a YAML file. It has a path towards to the Zephyr workshop. And in the Zephyr workshop repository, we can see REST YAML. And in this file now we can see all the references. Like we use Zephyr, and we use Zephyr in revision in version 3.4. That's the most recent stable version. We could also use the most recent main branch, for example. Then it will update automatically to all the to the most recent version. And we have here some hardware abstraction layers which we include. Today we would only need the hardware abstraction Nordic. And you can allow list and block list modules here. So we updated the manifest file. Now we can make West update again to update all the configuration on the repositories to this particular version, which was specified in the manifest file. Okay, that's it. Now to run the samples, we could go in the Zephyr workshop. And here you can see samples and slides. We are just interested in the samples right now. And the first example is Hello World. Benjamin also mentioned that there is a QEMU emulation. So right now we want to try the samples without a board. So you can all try that out, even though you don't have a board at hand right now. Those first few examples will work without a board. So West build B for board. Our board is currently the QEMU Cortex M0 emulation. And we use the samples directory, Hello World sample. -P makes a clean build. There we go. And now you can see West configuring CMake and now running the compilation. Now the compilation has been done. You can see here the file size is 1.5 kilobyte of flash and RAM is 3.9 kilobyte, so it's fairly small. To run it, we just type West build -t run. And we can see Zephyr has been booted. We have the version that we specified in our manifest file, Zephyr version 3.4, and Hello World, and it detected the board, the QEMU Cortex M0 emulation. Okay, maybe at that point we can pause for 5 minutes so you can catch up on the samples, and then we can make a survey and see how many people got the setup running. What do you think, Avik? Is this should we do that? Should we give it some minutes to wait? can show the slides, then you have the reference to the commands. Okay, I see most people are currently doing the installation. That's, yeah, that will take some time, some minutes, I think. So let's take some minutes and give that time. Oh, I'm muted. Maybe, Avik, you can give me a hint when around 30% maybe of the audience have a setup running, and then we could move ahead, and then people could pair up, do the examples now together, and then later they can sit together and install it. What do you think about that? Akasha, yeah, of course, sorry. So what do you think about that? Should we do like that? Is some people getting their setup running? Okay, yeah, we can proceed and have a reference at the examples, and then at the end we will see how much, I mean, whether we have time for continuing the setup. All right. So the next sample would be a logging sample. Zephyr has a logging module. And the specifics of the logging module is that you can have different log level, debug information and error, depending on how much information you want to print while the firmware is running. So again, we run this on simulation. It's the second example, logging. And we make a clean build again. And then again, rest build. Yep. This is the sample running in emulation, showing the logging. You can see here the different log level. We have error log level, debug log level. One specifics in the debug log level, you can see it also prints the function it is on. Like this is the file, and here we have the function, the main function, and inside the main function, it prints the debug string. So now we can just go into code and see how that looks. I think it's better to show in one. So here we can see the different log levels. Log debug, that was the string we just saw. And we can see they're all in main, but only for the debug log level, it has been printed the main function as well. That means debug log level, debug messages will be a little bit more talkative and tell exactly where they have been executed from. In between, we can have a look at how samples are generally represented in Zephyr. We have, this is one sample. We have a source directory. We have a CMake lists that we can have a look at. CMake lists is configuring CMake. And for example, here we can see target sources. It assigns the sources which will be used to build that sample. And it finds the Zephyr base as a reference and builds the whole operating system plus our sample. This whole setup is called an out-of-tree example. It means we have Zephyr, the Zephyr repository in one place, and in another place we have our application. And typically in products, this is what you want. You want the operating system independent from the operation, from the application, so you can segregate them in different repositories. Next sample would be work queues. Let's build that again. Okay. Here we can see there are different work items, and okay, I think I should. Yeah, first some words about work queues. So work queues are queues which run on threads, and those work queues, to those work queues you can assign work items. And basically work queues are a tool to separate interrupt context from thread context. If you have a function which you want to run after a button has been pressed also, you typically don't want to run this function in interrupt context, at least if it's doing a little bit more. And then you start a work queue within the interrupt context. And afterwards, the work item gets scheduled for the next thread, and then it will be executed. So for that, we'll have a look at the source code, and it's easier to explain. So we have, I think I need to make it a little smaller. Yeah. So we have a work handler. This is our work item. Like this is the function we want to run whenever we have a task to do. And in this work handler, in this example here, we get the current thread. We get the thread name, and we check in which context it is running. Are we running in interrupt context, or are we running in thread context? And if yes, what is the thread name and the thread priority? That's all the work handler in this example is doing, just to visualize what kind of runtime context we have here. Then jumping to main. Initially, we have, First, we run the work handler, the function I just showed, our task that we want to do. We run it in main. So we should see there would be the first one which runs in main context. Afterwards, we submit it to our work queue. And per default, there's always a system work queue. Zephyr always runs a system work queue. And this is what this task gets assigned to. So if you look at the output of the terminal, we can see the first one is running in the main thread with a priority 0. The second one is in the sys work queue. That's our default system work queue with a thread priority -1. Afterwards, we can create our own custom work queue, for example, with a different priority if you have different. In our case, this priority is my priority, and that should be 5. We defined it here in the very beginning. It is 5 with the task stack size of 512 byte. We can allocate a name, my work queue thread. And afterwards, we submit the work item to that particular work queue we just created. And we can see that here. My work queue thread with a priority of 5. And here it's important to know that negative priorities are cooperative tasks, and positive thread priorities are preemptive tasks, like tasks that can be interrupted. That means the higher the number of the priority, the lower the actual priority is. And that is also documented in the Zephyr documentation. Next one, we start a timer. It's called my timer. The timer runs one time, and after 1 second, it should expire and run this timer handler. You can see here, timer expired. In this timer handler, we directly run the work queue handler. That is the work item we want to execute. And afterwards, we execute and we schedule this work item in our default work queue. And we should see different runtime contexts. This function should be running in interrupt context because this is our task handler, which runs as an interrupt. And afterwards, we should see the work queue context. And this is exactly what we see here. The timer expired. First, the normal work item gets executed, which is in interrupt context. And then afterwards, the scheduled work item is executed, which runs in the system work queue. And this is the important thing to notice here. Typically, you don't want to run much things in interrupt context, but in interrupt context, you can easily start work queues and schedule them for running after the system is out of the interrupt context. Okay, are there any questions for the work queue example? Okay, then go ahead. Okay, next example is shell. And Zephyr has an integrated shell. That means it's a shell where you can type commands and those commands get executed. And this is quite interesting and gives us some information about the running Zephyr instance. So we built the example again. Again, shell can also run in simulation. And we run it. Typo. Yep. So this is our shell. With tab, we can see the commands, and we can autocomplete the commands. And we can check, for example, what is the version. Version is Zephyr, version 3.4. That's correct. And now we can look into which tasks are actually running currently. And for that, we type the command kernel. Again, tab is autocomplete. And then let's have a look at the threads. And again, here you can see our default system work queue with a priority of -1, where you can schedule work items on. Afterwards, we have the shell UART, like a driver for the UART. We have logging. Logging is also handled in a thread, usually per default settings, that if you emit some logging messages, they actually don't cause delays, but they get scheduled for once this thread is finished running, and afterwards your log messages are getting printed to the terminal. And of course, we have an idle thread. If nothing else is running, then the idle thread will running. And if you look at the execution cycles, most of the time our system is an idle. 99% of the time the system resides in idle. And if it would run on a microcontroller, this 99% of the time the CPU can sleep, you can switch off all the peripheral, you basically consume a very little energy. And again, in the shell example, there is a good documentation. You can easily add own commands, like you can, for example, test device drivers with it. When you have your application, you can still implement some shell commands, and while the application is running, you can probe your driver, you can get a sample from it, or do any other commands. Okay, I see there are now some people able to run the blinking LED. That's great to know. We could also continue running the shell command. So for that, yeah, this is the blink example, and you have run the samples basic blinky. Now let's have a look at the samples. And I think that's better to do in the repository itself. So to run the shell module, this is also in the normal Zephyr repository, sample subsys shell module. So you can make west, build, board. This would be the command to build it, to build the shell example in the normal Zephyr repository. Because I think that's what you set up right now. Initially, you set up the normal Zephyr repository, and from there you can run it. And we can run it again in simulation. And there we have our shell. So it's that easy to run samples. Okay, sure. I would have two more samples, but we don't need to show them. It's one is Bluetooth, and the other one was the sensor example. But feel free to continue hacking. I think you got a good start, and if some people got the setup up and running, that's great. And then make sure to help all the others that everyone has a running setup later. Yeah. Okay. Thanks, everyone, and thanks for the opportunity. Are there any questions?